Last call for voting. For those of you that didn't see the vote poll, you can just PM me privately. That's fine. All right, so you guys are pretty tight. We've got 53% of you guys said accurate and 47 of you guys said precise. All right, get ready to justify your answer for points. Let me just point out that you can drop it in chat. You can private message me. You can use your voice. All of these will count towards your grade. So the question was, which would you prefer? The pilot of your flight is consistently accurate or precise? You gotta answer one way or another because you only got choice of 2 pilots. All right, so who wants to justify their answer first? Let me just point out also that there are no wrong answers here.
I'll go. Okay, so I said precise because when the pilot is landing, if the pilot is accurate, I feel like I don't know how to explain it, but I feel like when the pilot is landing, I feel like precise, the pilot's gonna land safer. And even if they're accurate with like where they're supposed to land, how slow they're supposed to go, they might not be as precise. But if they're just precise, then they're just gonna land safely.
I hadn't thought of it that way. That's interesting. So you're saying there, the plane is more precise than it can be more accurate. That's interesting. I like that one. All right, somebody else.
I said accurate, and I said I want the pilot to be more accurate because like if they're more accurate to like where they're supposed to land and like how they're supposed to land, then it'll be safer than being precise.
Right on. Okay. Argument for safer with accurate. All right, come on, guys.
I said precise because I feel like precise means more carefully. Like you could be accurate in landing, but maybe go too fast. And I feel like precise covers all those subjects.
Ooh, okay. So both of you guys are kind of saying the same thing about precision. One person said it's more exact. Yep. We're going to talk about that. All right, somebody else.
I put down precise because he knows what he's doing, and it's like much more. How to explain it? He just knows what he's doing more than accurate because it's just
So he's reliable.
yeah, basically.
Cool. Who else? You can hop on the same bandwagon. That's fine. Just let me know what your justification is. Either way, using your voice or chat work.
I said precise because accuracy is like being decent and being precise is like on point.
Cool, cool. Yeah, you're on the right track, in my opinion. I see someone said accuracy because if you could land more accurately, you could adjust your landing. Very good. Someone also pointed out that accuracy is a general area, not to be trusted, versus precise. You know what you're going to get. Yep. Who else? Come on. People are saying details. Yep. If you know what you're doing, you know the fine details, probably you're going to be safer. All right. Who else? What you got?
I said precise because being accurate, you could land like on the landing strip, but like you could land in the wrong lane and still crash into another plane. But if you're precise, you can land in the landing area and still land in your right lane and be fine.
Ooh, okay. Yeah, I like that. If you're hitting the tarmac either way, you would rather be accurate. All right. I see one with the pilot is trying to be as safe as they possibly can. Okay, so they may not be reliable, but they are trying. Very good. At least you're in the right area. Cool, cool. Any other responses before I close this? You are getting credit for this. It's 10% of your grade. You can private message me. Hold on, just going through, making sure I get you guys for credit. All right, I got all of your answers. Thank you so much. I see a lot of good details. All right, we're actually going to cover what the difference between the two are. And you don't have to go anywhere. I'm going to play the video for you. So give me just a second to bring that up. Okay, I can actually.
As the story goes, the legendary marksman William Tell was forced into a cruel challenge by a corrupt lord. William's son was to be executed unless William could shoot an apple off his head. William succeeded, but let's imagine two variations on the tale. In the first variation, the Lord hires a bandit to steal William's trusty crossbow, so he is forced to borrow an inferior one from a peasant. However, the borrowed crossbow isn't adjusted perfectly, and William finds that his practice shots cluster in a tight spread beneath the bullseye. Fortunately, he has time to correct for it before it's too late. Variation 2. William begins to doubt his skills in the long hours before the challenge, and his hand develops a tremor. His practice shots still cluster around the apple, but in a random pattern. Occasionally, he hits the apple, but with the wobble, there is no guarantee of a bullseye. he must settle his nervous hand and restore the certainty in his aim to save his son. At the heart of these variations are two terms often used interchangeably: accuracy and precision. The distinction between the two is actually critical for many scientific endeavors. Accuracy involves how close you come to the correct result. Your accuracy improves with tools that are calibrated correctly and that you're well trained on. Precision, on the other hand, is how consistently you can get that result using the same method. Your precision improves with more finely incremented tools that require less estimation. The story of the stolen crossbow was one of precision without accuracy. William got the same wrong result each time he fired. The variation with the shaky hand was one of accuracy without precision. William's bolts clustered around the correct result, but without certainty of a bullseye for any given shot. You can probably get away with low accuracy or low precision in everyday tasks, but engineers and researchers often require accuracy on microscopic levels with a high certainty of being right every time. Factories and labs increase precision through better equipment and more detailed procedures. These improvements can be expensive, so managers must decide what the acceptable uncertainty for each project is. However, investments in precision can take us beyond what was previously possible, even as far as Mars. It may surprise you that NASA does not know exactly where their probes are going to touch down on another planet. Predicting where they will land requires extensive calculations, fed by measurements that don't always have a precise answer. How does the Martian atmosphere's density change at different elevations? What angle will the probe hit the atmosphere at? What will be the speed of the probe upon entry? Computer simulators run thousands of different landing scenarios, mixing and matching values for all of the variables. Weighing all the possibilities, the computer spits out the potential area of impact in the form of a landing ellipse. In 1976, the landing ellipse for the Mars Viking lander was 62 by 174 miles, nearly the area of New Jersey. With such a limitation, NASA had to ignore many interesting but risky landing areas. Since then, new information about the Martian atmosphere, improved spacecraft technology, and more powerful computer simulations have drastically reduced uncertainty. In 2012, the landing ellipse for the Curiosity lander was only 4 miles wide by 12 miles long, an area more than 200 times smaller than Viking's. This allowed NASA to target a specific spot in Gale Crater, a previously unlandable area of high scientific interest. While we ultimately strive for accuracy, precision reflects our certainty of reliably achieving it. With these two principles in mind, we can shoot for the stars and be confident of hitting them every time.
All right, so my question for you guys was the shaky bow accuracy or precision?
Precision.
Very good, very good. Why was it precision?
Because there was no way of telling where the shots were going to land. So he had no way to rate his accuracy.
All right, well, they did cluster around the same spot, so that's precision.
Oh, okay.
Oh, I'm sorry, I heard what you were saying. So precision is where it's the same spot, but accuracy, I'm sorry, I put the definition around here. Yeah, accuracy is it clustered around the right spot. I'm sorry, I have these backwards up there. So with the shaky hand, he was all over the place, right? So with the shaking hand, he has low precision, but it was clustered around the same spot, so he couldn't hold it correctly. But he was a marksman, right? So he still had some idea. He was in the general area. All right, so this is what I want you to write down. These are the two main words today, is accuracy, which is the closeness of your measurement to the true value, or target in this case, but your true value. So like the guy in the observation video was talking about rings in Saturn, and until they became more precise, they couldn't become more accurate because of the tools. So accuracy is closeness to the answer, the correct answer. Precision, on the other side, is how fine your instrument is, how close your shots are together. So how close your data really is. And the nice thing about precision is if your instrument is precise but not accurate, you can calibrate, you can fix the device or tool or apparatus, they're all the same thing. You can calibrate it so it's actually in the right direction, so you can fix that. Whereas accuracy, you have to worry about precision. If you're high accuracy but low precision, there's more that needs to be taken care of. So here's some examples. Accuracy is low in this first one, and precision is low. It's just all over the place. Accuracy for this one is low, but your precision is high. That's where you could calibrate your instrument to get it. Well, if you're hitting it in the same place, right, we can fix where we're pointing it. Accuracy here is high, but precision is low because clustering around the true value, but only getting it some of the time. So the accuracy is high, but they're not close together. There's no insurance. And then here, where it's clustered together right on the target, that's high accuracy and high precision. So clustered close together, high precision. In the right area, that's accuracy. All right, so this is not the version I wanted to put up, but here's what I need you guys to do right now. Ignore the bottom part of this for right now. I need you to grab 3 sheets of paper, a ruler, a scrap sheet, and you're going to need a table, a flat surface. So go ahead and get those things now. All right, for those of you who have your things together, here's what I need you to do. You're first going to make your target, which is a piece of paper down here with a dot in the middle. Okay, so you can see my mouse. Cool. So this one right here is your target. And then you're going to crumple up 10 of these little balls of paper, about the size of a penny or less. So go ahead and do that first.
What do
All
you
right.
want us to do first?
So the first thing you're going to do is you're going to go ahead and make your target, just a dot in the middle of the paper, and crumble up 10 tiny balls, little ones. If you've already done that, you can move on to the diagram step. That's these right here, which is just 2 pieces of paper with 4 boxes. These are going to be your diagrams. And if you can see the picture close enough, up here it says experiment 1, trial 1. Over here it says experiment 1, trial 2. And down here it says experiment 2, trial 1, and experiment 2, trial 2. And then the same thing down here for 3 and 4. So for each part of this experiment, you're going to do 2 trials, and 2 trials are going to consist of 10 paper balls. So 10 paper balls per trial, and we have 4 experiments. Everybody good? All right, I'm going to switch pages here. I will leave this PowerPoint, by the way, in your, that's fine if you're not ready. I will leave this in Google Classroom. It will have all your examples and the experiments, so you can do this at your own pace. Some of you guys may say, well, I don't have a ruler. What you can do is use a lined sheet of paper and use that for your units when we're measuring. You do need some sort of measuring device. You can also use your phone if you like. There are some measuring devices you can download or web pages you can go to. And you can also, worst comes to worst, you can use your fingertips, all right? From the joint to the top of your finger. That's another way you can do it. If you do it that way, and whenever you're measuring, please make sure you tell me what unit, what are you measuring? Because if you just said, oh, it's 16, well, 16 fingertips, 16 lines on a paper, 16 inches. You can use any unit you want to use. You don't have to use metric right now.
So do we draw the dot in the middle of each thing?
Yeah, so for the first one, it's in the middle of a blank paper. And then for the diagrams, it's in each box, middle of each box. All right, so that's my target right here. I'm going to be throwing these paper balls at it. You are going to do that too. And I'm going to do 10 of them. Here's 4 of them right now. And then once you've done that, right, you'll have these diagrams like that. And what you're going to do is you're going to make little X's where your shots fell. So, and you're going to estimate these. Now, if you, if it goes off the table, you're just going to put an X on the side or a star. I did a star there. Right. Right. So if it goes off the table, that's fine. Just give me the direction. Most of mine go off the table, by the way. I'm a horrible shot. All right. So I'm going to move into the experiment. If you're not sure, this will be there with my examples. And we'll do experiment 1 because it has the most directions. Okay, so each trial contains 10 paper balls. You're going to be measuring the distance of the paper ball. You're going to leave your data. There's a Google Docs and Google Classroom, and you're going to drop your data right in there. And then the diagram is what you're going to also upload. You can take a picture of it, however you want to do it. Be brutally honest or the experiment doesn't work. I'm not going to be sharing your name or work with anybody. All right, so experiment 1. This is why I say no, no dishonesty here. What you're going to do is close your eyes and turn around safely twice. If you can't do this, you can just have somebody set the paper in front of you with your eyes closed, and you can try to place the paper balls in the right place. All right, so once you've turned around safely twice, you're going to keep your eyes closed. Your paper balls should be in your hand, and you're going to try to put the balls on the piece of paper without feeling for the paper at all. And you're going to do this twice. Your first trial will be 10 paper balls. You're going to measure them and do your diagram. And then you're going to do it again with 10 paper balls. You're going to measure how far from the target dot you made it, and you're going to create a diagram. Then you're going to record your measurements to the Google chart and draw a general diagram. It doesn't have to be perfect here. You cannot, for any reason, if the ball falls off the table, label your measurement, the part that you're going to write in the table, as infinite. Below that, you see that sideways figure 8. That's the symbol for infinity. I'm going to quickly just go through the other experiments so you see me talking about them. Experiment 2, you're going to, with your eyes open, try and drop the paper balls 1 foot. You can estimate this above the dot. You can use your ruler to estimate if you want. You're going to measure how far away each paper ball is from the dot. And then you're going to record that data in the chart and draw your general diagrams. You'll have trial 1, trial 2. Experiment 3, with your eyes open, you're going to try and place the paper balls on the dot, measure how far away they are now, and then you're going to record your measurements. And then experiment 4, this is where some of you guys are good shots. Stand 5 feet back or as far back as you can, and you're going to try to throw the paper balls at your point. You'll be measuring them and putting them in the Google chart, and then drawing that general diagram. That general diagrams is this right here. And then, of course, clean up so your guardians don't get mad at you for having paper balls all over the place. So I'm going to back up to experiment 1. This is not letting me move that window. I apologize. So you guys can get started. If you don't finish, you'll just work on it today and tomorrow. It'll be due Saturday. Oh, and just so you know, it will be assessment points. I think there's some post-lab questions in there. So you just do this lab, answer the post-lab questions honestly and thoughtfully, and you can have your assessment points.
So you say you're gonna post it on Google Classroom?
Yes, absolutely. I'm posting it right now.
Okay.
All right, it should be there. Also, guys, I want to point out that if you can't connect for whatever reason, just let me know. There is a YouTube live version and I'll be hanging out here. If you guys got the idea and you want to head to Google Classroom, I'm not making you stay. You are fine to go off and do your experiment. Thank you so much for coming in. I really appreciate how active you guys have been. Also, enjoy your weekend. I will be here for the next 15 minutes, not going anywhere.
So how many experiments we got to do?
So it is a total of 4 experiments with 2 trials for each experiment. And you can just drop your measurements straight into that chart. You don't have to write them all down and take a picture. The only thing you're taking a picture of is your diagrams. So you should have 8 diagrams. Each box is a diagram.
When does this due?
Okay, this is due Saturday before 11:59. Let's make it 11:59.
Oh, okay. Thank you.
Yeah, yeah. Cool. It is due on Saturday at 11:59 p.m. there's no further questions, I'm gonna there's no further questions. I'm gonna go ahead and end this share. Thank you so much for joining.